the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are just stepping into probably the most advanced material that they have seen so far in all of mathematics. And when I say advanced, I don't mean difficult, I just mean theoretically advanced. This material, which is vector spaces, really is the gateway into advanced mathematics. In fact, I have a little paragraph on the previous page to this, which says the following: "It is now time for us to see what makes our number system work. We're about to delve into the underpinnings of mathematics in a way that most individuals have not seen. The game," and let me highlight that word, the game of mathematics is predicated on 10 rules that we call axioms. These axioms beget arithmetic, algebra, trigonometry, calculus, differential equations, and linear algebra, and many more courses beyond this course. Welcome to the beautiful world of real mathematics. Everything you've learned up to this point really relies upon the 10 axioms we're going to lay down in this video. Now, going back to our page on vector spaces, let's go ahead and define what a vector space is. And I'm going to read this very first paragraph and then go back through and talk about pieces of it. So, a vector space V is a non-empty set of objects, which we will call vectors, on which is defined two operations, addition and multiplication by scalars. These are subject to the 10 axioms listed below. Now, before I go into the 10 axioms that these two operations are subject to, let me dice apart this paragraph a little bit more. So without calling it a vector space, let's just say we have a set V. And we're going to assume this set is non-empty. That's critical. We must have a non-empty set to begin with. Now, just to let the cat out of the bag, every vector space actually contains the zero vector. So by virtue of being a vector space, it will always have at least that one element. So it will be non-empty, I promise. So that chunk or that set of items contains a bunch of things that we will call vectors. And we are kind of used to that right now, that we've been working with sets of vectors up to this point. However, when you're working with spaces after this course, they do not actually have to be called vectors, the elements within these sets. But for right now, when we're dealing with a vector space, we will call the elements vectors. Another thing I need to draw your attention to is, despite the fact that we're calling them vectors, they will sometimes, and in fact often in this video, not even look like vectors to you. They will look like functions, like polynomials or something like that. We're still going to call them vectors for this entire video, and actually for pretty much the rest of linear algebra. That'll seem awkward at first, but you get kind of used to it as we move on. Anyhow, we have this set of vectors. It's non-empty, and we're going to define two operations for all objects or all vectors in this set. And those two operations are addition and multiplication by scalars. And just to let you know, when I say scalars, you already kind of know what a scalar is, or at least you have been told that a scalar is just like a real number or a complex number. But to be honest with you, scalars are objects from an underlying field, which does not have to be the real numbers, nor does it have to be the complex number system. It could be a completely different number system. But in linear algebra, for right now, we're going to have the field or the underlying field be the real number system. It could be, by the way, the complex number system. Everything will still work out fine. However, like I said, we're going to stick with the real number system for this course. It's not required for you to know what a field is, even though I actually define it or at least mention the word field down there. You are not required in a first-year linear algebra course to understand what a field is. So don't worry about that. Anyhow, we have a non-empty set of objects. Each of those objects we're going to call a vector. And we define two operations for all those objects within that set of vectors. And those two operations are going to be addition and multiplication by scalars. And we're going to have a strong requirement that those two operations follow a rigid set of rules that we call axioms. If it is the case that that set of vectors with those two operations follows the set of axioms that we're going to list down below here, those 10 axioms right there, then that set will be called a vector space. And there are some very important properties that we gain from a set of objects that is a vector space. So having a set of objects be a vector space is going to be very powerful for us in the long run. To have this conversation, we must first assume that we've been given at least a few vectors within our set. So suppose u, v, and w are elements of this set of vectors. They are vectors. And suppose that c and d are scalars in the underlying field. Again, we're going to assume that the field we're working over is the set of real numbers. And I want to reiterate, it is not a requirement that you know what a field is at this point. That is usually left for a higher level math course, an upper division course of mathematics. Finally, we start into what makes this set of vectors a vector space. The first and most important two axioms are going to be axiom 1, which, by the way, I just number these this way, but you might be learning from a textbook that doesn't number them at all. So your textbook, in fact, all textbooks will likely call this closure under addition. And the second most important property is closure under scalar multiplication. Those two are, in my opinion, the top two properties to look for first. So what does that mean? Closure, first of all, what does closure mean? If you have an operation on a set of objects and you say that set of objects is closed under that operation, that means when you apply that operation to a couple objects within that set, or in the case of scalar multiplication, if you apply that operation against one vector within that set, the resulting summation or operation, which could be scalar multiplication, will land you right back into that set. That is, if you grab a random or arbitrary u and v from the set v and you add them together, that sum should be within that set as well. For example, the set of integers. If you grab any two integers, let's say -1 and 10, the sum of -1 and 10 is 9, which is also an integer. So it looks like, although that's not a proof, it looks like the set of integers is closed under addition, because when you add any two integers, the result is yet another integer. Likewise, looking for closure under scalar multiplication, it just says if you grab any number from our underlying field, the real number system, let's just pretend, and you multiply that against any vector, any arbitrary vector within your set V, that product should also be within V. Now let's go ahead and think about that example I just said out loud about what if our set is a set of integers. We've already said that that set of integers is actually closed under addition. If you add any two elements from this set, their sum will also be an integer, so their sum will be within this set. However, if the underlying field that you're pulling other numbers from, specifically your scalars C, if that underlying field is the real number system, then if you had that set of integers, it would not be closed under scalar multiplication. Why? Because pi, which is a scalar from the real number system, times 3, which is an integer from our set V, is going to be 3 pi, which is not an integer, so it's not in V. So therefore, the set of integers is not closed under scalar multiplication, where your scalars come from the set of real numbers. However, if you do have a set V, where any scalar multiple of a vector from that set V lands back into that set V, then you know that set V is closed under scalar multiplication. You essentially just want your operations to land your vectors back into that set V. If that's the case, you have those first and sixth properties satisfied, which I, again, consider to be the two most important. You might ask yourself, well, if they're the two most important properties, why did you list closure under addition as the first and closure under scalar multiplication as the sixth? That doesn't make sense. Well, it does make sense, actually, because I list all the addition properties first, and then all the multiplication properties second. That's just the way I like to list things out. What else is required for that set to be a vector space? Well, let's deal with just all the additive properties at this point. You need to have the commutative property of addition. That is, for any two vectors within your set V, the sum of u and v should be the same as the sum of v and u for any two arbitrary vectors u and v in your set V. You also need the associative property of addition, which means for any vectors u, v, and w from your set V, if you decide to add u and v first and then add that result to w, it should be the same as adding v and w first and adding that result to u. If both of those properties are satisfied, you're well on your way to having your set be a vector space. It is not a vector space yet, but it's well on its way to being a vector space. You also need an additive identity. That is, you have to have a zero vector, because 0 plus any other vector u is going to be u. So you want some vector that will call 0 to exist within your set of vectors, such that if any arbitrary vector from your set V, which we will call u, plus that vector we're calling 0, should result in the original vector u. This works very much like our arithmetic. In arithmetic, there has to be a number 0 such that any number plus that 0 should return the original number. In fact, all of these axioms are straight from your arithmetic course, to be honest with you. Think about the real number system. If you add any two real numbers, it's still a real number, so we have closure under addition. In the real number system, a plus b is the same thing as b plus a. In the real number system, a plus b then plus c would be the same thing as a plus the quantity b plus c. Again, in the real number system, there must exist a number 0 such that a plus 0 is a. And finally, in the real number system, for any real number, a, there should exist an opposite number, negative a, such that a plus negative a is 0. And that is true. We know that about the real number system. And by the way, that last one, which is the additive inverse axiom, also should hold for vector spaces. For all vectors u in our set V, there must exist the opposite vector of u also in our set V, such that when you add those two vectors, they become 0. Now, right now, the notation is such that you would say, well, duh, that just totally makes sense to me. But I'm letting you know, as you advance through mathematics, these equal but opposite vectors need not look opposite. It just depends on how you define addition and how you define scalar multiplication. And yes, you can define addition and scalar multiplication differently than how you've had it defined your entire life. If you want to know how, take a course in number theory. It's really fascinating. And there are actual number systems still being created to this day that have different definitions for addition and multiplication than we're used to. And those other number systems end up being very useful for many problems in computer science and physics and mathematics. Again, that's not the purview of a linear algebra course, at least not right now, but I just want to say it to pique your interest into the possibility of taking a higher level course in mathematics if you so choose to do. All right, let's step into the multiplication axioms, and we've already talked about closure under scalar multiplication. We require that. But then we have two multiplication properties glued together. And I do this on purpose because I really find the distributive properties to be sort of the same. They look the same to most students. They feel the same. One is distributing a single scalar to two vectors from your set V. So we need the following to be true for all arbitrary vectors u and v in our set V. That c times the quantity u plus v is cu plus cv. And you've done distribution long enough to know how that's done. But we also need the second one where we have two scalars from our underlying field multiply a single vector. C plus d times the vector u should be equal to cu plus du. If those two properties are true, along with the previous 6 properties, then you're well on your way to having a vector space. But it's the last 2 here that we'll need to finish out with so that we actually have a vector space. Axiom 9 is the associative property of scalar multiplication. It just tells us if you have a couple scalars in your underlying field and you multiply that against a vector u, well, c times the quantity d times the vector u is the same thing as c times d times the vector u. Again, if that's satisfied, you're well on your way to having a vector space. And finally, we need a multiplicative identity. That is, our underlying field must have a unit, which we shall call 1 here, such that when 1 is multiplied by any arbitrary vector in our set, it results in that vector. Now again, a lot of students first see this as being obvious. That's because I'm using pictures that mimic our number system. That picture, 1, we're so used to thinking of it as, well, 1 times any number is just that number. However, it could be the case that you're dealing with a field, an underlying field, where the version of 1 that exists in that field doesn't look like 1 at all. It could look like something else completely. It doesn't even have to look like a number. It could look like a symbol you've never seen before. But again, that's well beyond the purview of linear algebra. So for now, I'll just say there just has to exist a number 1 such that 1 times any vector in our set V becomes that same vector from our set V. If all 10 of those axioms are satisfied, then we definitely have a vector space. And again, some very special properties come from having a vector space. Now I have a little note down here. These axioms must hold for every vector in the vector space and all scalars in the underlying field. If you can provide a counterexample of one vector for which one of these properties or these axioms does not hold, then your set of vectors is not a vector space because there's at least one vector within it that, for example, might not satisfy closure under addition or might not follow the associative property of addition or something like that. Now, as we generally do when we deal with definitions and new kind of topics within mathematics, we generally follow that with a theorem, something that says, okay, well, with this information, here's an extra little oomph that we get from it. And in this case, that extra little oomph is this theorem right here. Let V be a vector space. For each vector u in that vector space, and any scalar in the underlying field, 0, and by the way, this 0 is from the underlying field, it's a scalar, so 0 times that vector u will be the 0 vector. And c, again, c is just a scalar from the underlying field. C times the 0 vector should be the 0 vector as well. And then notationally, this last one is kind of obvious. The opposite of the vector u can be rewritten as -1 times the vector u. -1 being from our underlying field. So I've gone back and forth about whether or not I want to actually spend the time proving one of these. And I think I will go ahead and just prove maybe the first one. And just to let you know, I am not practiced on this. So I haven't set up behind the scenes and figured out how this is done. I'm just going to make this up as I go along, which is always a dangerous thing. But I want to show you kind of the process of how a mathematician might work. So I write down to the world that I'm about to do a proof, but then every good mathematician off to the side does some scratch work. And this scratch work is literally something you would never show anybody else, just how you're going to detail out your proof. So it's all your kind of messy work before you get to the actual proof. And if I want to prove this guy right here, let me go ahead and just say, I want to show, that's what WTS means. I want to show that 0, the scalar 0, times any vector u from our set of vectors should equal the 0 vector. Now I'm allowed to assume that I have a vector space, right? Because let V be a vector space is the very first sentence. So I'm going to go ahead and assume that all 10 axioms are satisfied. There are two ways to go about this that I can see offhand. I want to either start on the left-hand side and eventually arrive at the right-hand side, or I want to start at the right-hand side and end at the left-hand side. The trick to most of these type of equation proofs is to start on the uglier of the two sides. So I'll start with 0 times u. And I'll take a look, again, doing some scratch work here. I want to eventually arrive at the 0 vector. Well, we know that 0, and I'll highlight it in red here, that 0 is from our underlying field. It's just a scalar, a real number. And I know a lot of properties of real numbers. For example, I know to get to 0, I could write that as c minus c. That's just a property of the underlying field. That's a property of real numbers. That 0 is the same thing as c minus c. So there's no real magic that I'm performing there. Now what I'm going to write next might be weird for a lot of people, but notice in our list of axioms that we do not have any subtractions. Everything is an addition, right? The only time you see something like a subtraction is when you're adding a negative. So I'm going to have to write our subtraction, specifically our distribution that we're going to do of c minus c times u. I want to write that as c plus something. So I'm going to go ahead and go back. And again, using properties of real numbers, I'll write that as c plus a negative c times the vector u. Now, because u is a vector from v and v is a vector space, I happen to know that we can use distribution here. And because I've just used an axiom, I'm going to go ahead and cite it off to the right-hand side. Some people will require you to write that as the distribution axiom number 2 or something like that, or they might have you cite which number within all of your axiom list that is, but I'm just citing it as distribution. There's nothing wrong with that. The next thing I'm going to do is rewrite this as cu plus a negative 1 times c times u. Again, that's just a property of real numbers. Negative c is negative 1 times c. But what I want you to zoom in on here is that this is a constant times the vector u, and this is the same constant times the vector u. And I'm going to note something off to the side here for myself. That red cu is just another vector from our vector space, because our vector space is closed under scalar multiplication. That is, if I took 10 times u, that would be within our vector space. It's just yet another vector. So that red ink there is like a vector. Let's go ahead and call it v for right now. Now I'm going to use a theorem that I haven't proved, and that theorem is this one at the bottom, but I just want to use the notation here. So I'm going to go ahead and use the fact that negative 1 times the vector v is just negative v. And yes, I know I haven't proved that yet, but maybe that's a homework item for you or something like that. I'm just proving the first one. And if you had to cite that, I don't even know how you would cite that. I'd say by this theorem. I have no idea. But I'm, again, only proving the top one. So please do not say, wait a second, you're using something that you need to prove within your proof. I will assume that you will have already proven that in a previous part. And I'm just using that here. Now, I happen to know I have an additive identity axiom that says if I add u plus its opposite, it should be 0, as long as we have a vector space. And that's exactly what we have. V is a vector space, so therefore v plus a negative v, the vector v, plus the opposite of the vector v, is going to be 0. And again, that's by the additive identity axiom. And notice what I've proven here is that the scalar 0 times the vector u is equal to the vector 0. In reality, I was trying to chicken scratch out what my proof might look like, but actually that's probably what the proof will look like. So if I were to rewrite the proof legitimately, I might do something like this. Moreover, I want to name that vector CU because I did that in my scratch work. Remember, I got to that vector CU at some point, and I decided to call that vector C times U by a completely different name. And in fact, I might use the name W in my proof because having two V's in my proof might be confusing to a reader. So call this vector W, that is, the vector W is just the constant C times the vector U, which is also in our vector space. Then we get this right here. 0 times the vector U is just C minus C times the vector U. That's a property of real numbers, so there's no explanation necessary for that, which is the same thing as C plus the opposite of C times the vector U. Again, it's just a property of real numbers, so we don't need to have to explain that, which is equal to C times U plus negative C times U. That is from our distributive axiom, or I'm calling it the distribution property, but it is the distributive axiom, or one of them, which is equal to C times U plus negative 1 times C times the vector U. That negative 1 times C is the same thing as negative C. That's just from, again, arithmetic. There's no need for me to describe that to the reader. It's like me saying to the reader, oh, negative 3 is negative 1 times 3. They should know that. However, this leads to C times the vector U plus negative 1 times the group C times the vector U. And you'll notice this is slightly different than my scratch work just because as I was writing this, I thought, well, I'll be a little more rigorous on that step and just include the fact that I'm grouping this stuff together instead of starting with negative C and then negative 1C, and all of a sudden I'm switching the multiplication to negative 1 times CU. I'm associating the multiplication differently, and that's an axiom we have written down. Some people will call it a multiplicative associativity axiom or the associative property of scalar multiplication, whichever you want. We had made the statement earlier that whenever we see the scalar C times the vector U, we're going to call that the vector W. So this is just a replacement step. And then the next step, I write that as the vector W plus a negative times the vector W instead of a negative 1 times W. And I put an asterisk there because that's actually to be proven later on by you or maybe by your professor or something like that. I'm just, for right now, assuming that we've already proved that. However, as long as you have a vector space and W is in that vector space, then W plus its opposite is going to be 0 due to the additive identity axiom. And therefore, we have shown 0 times the vector U is the 0 vector. QED, quod erat demonstratum. So it has been demonstrated. And this is pretty much how all of these proofs are going to go. But notice the creativity used here. I always start with a little bit of scratch, and I want to slowly work my way through using the properties of real numbers as often as I can, because those I can assume, and including the axioms because we're working with a vector space when I have to. Now, before we leave this video, I should actually do a full example. So let's take a look at a very weird feeling example. And I kind of like this example because it really showcases how off the cuff you have to feel with this type of theory that we're going through right now. And what I mean by off the cuff is that we're not going to painstakingly go through each of the axioms and prove them with such precision and rigor that it's mind melting. Instead, we're just going to resort to our knowledge of polynomials here. And I should pretty much read the problem first before I continue talking about what we're dealing with. So let's go ahead and look at the example. Show that the set P sub n, which is a set of polynomials of degree at most n. Show that that's a vector space. And then use this to motivate why the set F, which is a set of all functions over the field of real numbers, is also a vector space. Now there's a lot to digest here. Probably the hardest part of a problem like this is that you have to get used to polynomials being called vectors. And contextually, they really are vectors. They exist within a vector space, which we're going to prove that P sub n is a vector space. And because they're elements of that P sub n, we can call them vectors. Well, let's go ahead and list out what P sub n sort of looks like. And to do this, I'm going to use set builder notation. P sub n is the set of all vectors, u, let's just call it that, such that u is equal to a polynomial of degree at most n. So I'll write this as this long polynomial right here, where a sub i's are real numbers or scalars, assumed to be from our underlying field, and n is a natural number. Actually, it could be a whole number. Now I'm using a weird notation for the set of whole numbers. The whole numbers are the set of natural numbers plus 0. And I often note that with a W with a double bar on it. That's supposed to be a double bar, it's just got a little thick ink there. But some other people write that as n, which is a set of natural numbers. And again, that ink is too thick, so let me make this slightly easier to read. N unioned with 0. So the set of natural numbers or counting numbers, 1, 2, 3, 4, and so on and so forth, union with 0. Or I've seen it written this way. Although I gotta be honest with you, that second way is not very common. Another way I've seen this written is z greater than or equal to 0. Set of integers greater than or equal to 0. But I've also seen it written as the double bar w. And that's kind of how I'm gonna write it. So anyhow, the set P sub n is equal to the set of all vectors such that the vector is an nth degree polynomial or a polynomial degree n or less, where the coefficients are scalars from your underlying field and the powers are whole numbers. Because a sub I are scalars, some of them could be 0. So in other words, a sub n, for example, could be 0, and a sub n minus 1 could be 0. All the way down to a sub 1. A sub 1 could be 0 as well. If that's the case, then all we would have left is a sub 0, which tells us that constants belong in this set of polynomials of at most nth degree. And that's because constants are technically considered 0th degree polynomials. Anyhow, that's just kind of a cool fancy notation that your text might use. Might not. Some examples of vectors within that set, x plus pi might be in that set of polynomials of degree at most n. Negative 3x squared minus x minus 4 could be in there. 12 could be in there because that's a 0th degree polynomial. And so on and so forth. There are an infinite number of polynomials within P sub n. Now we want to show that P sub n is a vector space. And as I mentioned when I talked about vector spaces and how they are defined, the two very important axioms that you should probably start with are closure under addition and closure under scalar multiplication. So I'm going to start with those two. Pay close attention to how I justify the fact that this is going to be a vector space. I am not going to grab an arbitrary polynomial from P sub n and then do a lot of math on it. The fact is, we have done mathematics on polynomials for years, so we're assumed to be experts with polynomials, but novices with vector spaces. But when somebody says, hey, I've got a bunch of polynomials, well, immediately I'm allowed to use every property I've ever learned in the past about polynomials in a conversation about this vector space. So to satisfy closure under addition, I'm just going to take a couple polynomials from P sub n and I'm going to mention something about them. And in fact, I'll start with the statement up here. Let u, v, and w be vectors, or in other words, polynomials in the set P sub n. I was just going to say in the vector space P sub n, but we don't know that is a vector space yet. So let u, v, and w be vectors within that set P sub n, and let c and d be scalars. Without even using u and v, I could talk about closure under addition. When I add two polynomials, the result will be a polynomial. Moreover, they don't gain power when you add polynomials. They may lose power. For example, x squared plus a negative x squared becomes 0, so it becomes a 0th degree polynomial, but they'll never gain power when you add polynomials. So the sum of polynomials having at most degree n is a polynomial of degree at most n. Therefore, we have closure under addition. The second property I'm going to skip for now because I want to get to closure first. So I'll say 2, 3, 4, and 5. I'll get back to those in a moment. But 6, which is closure under scalar multiplication, I want to talk about. Again, the vector space is new to us, like proofs of vector spaces and stuff like that. But polynomials are not. We can easily just state a constant multiple of a polynomial of degree at most n will be another polynomial of degree at most n. By the way, it may not have the same degree. For example, 0 times any polynomial reduces that polynomial to the 0th degree polynomial, but it's still a polynomial of degree n or less at that point, so we're okay. So we immediately know that our set of vectors, which are polynomials, is closed under addition of vectors and under scalar multiplication. Now we have to go through the rest, and the rest happens very quickly. Properties 2 and 3 are the commutative and associative properties of addition, and we know that polynomials, just from our history, we know polynomials satisfy the following. And notice what I'm saying here. They satisfy those trivially from properties of polynomials from our previous work in mathematics. Be very, very sparing with this word trivial or trivially. I don't want to see students walk around and saying, well, the proof of that is trivial, because that's very hand wavy at times. But to be honest with you, it is true. We've worked with polynomials so long that it is trivial to just say, listen, the polynomial p of x plus q of x is the same thing as q of x plus p of x. And likewise, we can showcase associativity. We've been using it for years, since elementary algebra, which is many, many, many years ago. So there's no need for us to therefore dig it up again. Property 4, or axiom 4, is that we require an additive identity. Well, 0 is in our polynomial space. I'll just call it a space, or a polynomial set of vectors. 0 being just a scalar 0, but we're going to call it a vector 0 for right now, where the vector 0 is actually just the number 0. And if you add 0 to any polynomial, it's the original polynomial. Again, I wrote trivially there because I'm saying we have done that for many, many moons. There's no point for me to go through and prove to you that x squared plus x plus 1 plus 0 is x squared plus x plus 1. There's just no real need for me to do that, or for you to do that. Likewise, if I give you a polynomial u, then there has to exist the opposite polynomial that is also of the same degree, to be honest with you. So it's also in p sub n, such that u plus that opposite polynomial u is going to be 0, which we are calling the 0 vector for now. So you can see how a lot of this seems very loose, very hand wavy here, that we're not doing a lot of rigor, but that's not true. It's just that we're pulling on our old mathematics, and so there's no need. It's for example, it would be as if somebody said, I need you to prove this, I don't know, big theorem. Okay, it's the squeeze theorem or something like that from calculus. And somewhere in there, you use the fact that, for some silly example, that 3 plus 4 was 7. Nobody expected you at that moment to prove that 3 plus 4 is 7. We assume you know that, right? So the same thing here. We assume you know properties of polynomials. Properties 7 through 9, which are the distributive properties, and then the associative property of scalar multiplication. I should hop back and show you those. That's these properties right here, 7, 8, and 9. Those properties, actually I could even say, and 10. 7, 8, 9, and 10, they are all true, because if you take a scalar times the sum of two polynomials, well, that's the same thing as a scalar times the first polynomial plus a scalar times the second polynomial. We know that. Also, if you have two scalars, c and d, and you multiply that against your polynomial, well, you could have taken c, multiplied against your polynomial, and then taken d and multiplied it against your polynomial and added those up, and the result would be the same. This property is almost so trivial that it's laughable to mention, but again, take a scalar c and multiply it against the scalar d times a polynomial, well, that should be the same as taking the scalars c and d and multiplying those first, and then multiplying them against the polynomial. And finally, 1 times a polynomial is just the polynomial. So therefore, properties 7 through 10 are satisfied trivially by polynomial arithmetic. Again, it seems very, very hand-wavy, like as if I'm not proving something, but I actually am. So since all 10 axioms are satisfied, that implies that P sub n is a vector space. So it adopts a lot of really, really cool properties that we haven't talked about yet. Now remember, there was still something else within this problem. We're going to use all of that to motivate why the set F, which is the set of all functions over the field of real numbers, is also a vector space. Well, replace polynomials with the word functions. We don't care about degrees here because, again, these functions do not have to be polynomials. They can be trig functions or logarithmic functions or exponential functions or radical functions. Doesn't really matter. But the sum of functions, well, that's a function. We know that from our previous algebra work. If you add the function u to the function v, it's the same thing as the function v plus the function u. Also, associativity is satisfied, so therefore, this is trivial from properties of functions. 0 is a function because if you graph y equals 0, it passes the vertical line test, so 0 is a function. And let me zoom out to make that f a little bit easier to read, where again the 0 vector is 0, thus take any function and add 0 to it, it's the same function, trivially. Also, for any given function that we have, there is its equal and opposite function, such that when you add the function to its opposite, they should cancel and become the 0 vector. We have closure under scalar multiplication because the constant multiple of a function is a function. Again, we're not worried about degrees here because we've stepped away from the idea of a polynomial. Now we're just keeping it general. And finally, 7 through 10 are still satisfied trivially by functional arithmetic. Hence, F, the set of all functions over the field of real numbers, is a vector space. Not bad. So that's all I really want to do in this video. I know it's somewhat long, but it's the introduction of a massively important topic, so it's good to take our time with it. I hope this video was a gentle introduction to vector spaces, and I hope to see you in future videos. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.